So this is the third numerical. In the CFD study, discretization error is 3%, modeling error is 6%, and round off error is 0.5%. Analyze the contribution of each error component and propose the detailed strategy to reduce the total error below 3%. Justify whether mesh refinement alone is sufficient. The error component analysis will cover the total error typically estimated by the summation of discretization error, modeling error, and the round off error. So what is the discretization error? This arises from the numerical approximation of the continuous governing equations, that is Navier-Stokes equations on a finite mesh. It is governed by the order of discretization scheme and the mesh spacing, that is delta x. So in this numerical, the discretization error is a 3%. So next error is a modeling error. This is a discrepancy between the actual physical phenomena and the mathematical model used to represent it. So common source includes the turbulence modeling, whether we use the RANS model or LES model or K omega K epsilon SST. So which simplified the fluid properties or idealized the boundary conditions. So here the modeling error is 6%, and round of error, which is a 0.5% in this problem. So this means from the finite precision of floating point arithmetic in computer hardware at 0.5%, this is relatively low, but accumulated in large scale transient simulation we use a single precision solver. We have seen the options available there: single precision or double precision. Okay, so current total error is the numerical error, that is the discretization error. The total error is summation of discretization error, which is the numerical error. Second is a modeling error, and third is a round off error. So 3% plus 6% plus 0.5%, it will give the total error of 9.5%. So whether this acceptable? No. We are expecting the total error should be less than 3%. Right? So is the mesh refinement only be the solution? Let's check it. So mesh refinement primarily targets the discretization error according to the Taylor series function expansion series. For the scheme of order P, the discretization error scales as numerical error equivalent to C into delta x to the power P. If we were defined to refine the mesh infinitely such that the delta x tends to 0, the discretization error would approach to 0. However, the modeling error and round off error are independent of the mesh density. In fact, round off error can be increased with the mesh density due to the higher number of operations. So even with the perfect mesh, means if we reduce the numerical error, that is discretization error tends to 0, the total error will be 0% plus 6% plus 0.5, which gives 6.5%. So since the 6.5% is less than 3%, so mesh refinement alone is insufficient to meet the target. So we have to apply the remaining, we have to define strategies so that we can reduce the modeling error and round off error. So to achieve the total error less than 3%, we must address the dominant error sources. In our case, modeling error is 6%, which is itself more than 3% of our requirement. So we must have the transition to higher fidelity physical model, as in if we use the RANS model with the standard K epsilon or K omega SST for better separation predictions, or we can go with the LES large eddy simulation if the time permits. So also we can improve the boundary conditions by using experimental data or validate the profile instead of uniform assumptions. So the target will be, we can reduce the modeling error from 6% to 1.5%. Now second is reduce the discretization error, which is at present 3%. Once the model is improved, we apply the grid convergence index, which studies to ensure the solution is mesh independent. So how can we do this? We can increase the distribution scheme order, that we can move from the first order upwind scheme to the second order or quick scheme. So it performs the systematic mesh refinement in the region of higher gradient, where we are defining the boundary layers or wake. Then target for this distillation error is 1%. That is, we can reduce from 3% to 1%. Then last error is a round off error. To ensure the double precision floating point representation, we can use for instead of single precision. So monitoring the iteration convergence to ensure the residual drop at least 3 to 4 or fourth order of magnitude, right? Iterative convergence criteria which we define in the software. So target of reducing the round of error is from 0.5% to 0.1%. So if we apply all the strategies, what will be the possible reduction in the error? As the total error after applying the conditions strategies, that is 1% for numerical error plus 1.5% for modeling error and 0.1% for the round off error. So total error is 2.6% after applying the strategies, so which is less than 3%. So we can say our strategies can be valid, it will be valid for the solution for present problem. So modeling error is primarily the issues. So mesh refinement is not possible, the solution for this case. So we can reduce the total error below the 6% by applying the strategies to the modeling error as well as round off error. So what we can conclude it that mesh refinement is alone is insufficient. Modeling error must be reduced to get the definite solution.